Welcome to Definite Integrals Part 1, Sigma Notation, where we try to add a bunch of things together and put it into a summation formula that makes it easy for us, because that's what the founders of calculus and leading up to calculus, the guys that preceded Leibniz and Newton, they needed a way to add a bunch of things together and compact the way they were adding those things together. So let me show you where the sigma notation is coming from. Alright, the idea, again, for an integral is to find the area under a curve between two x values. And what was happening is that they were dividing up this interval into little sub-intervals and then using a limit formula to add up all and make the width of each one of these intervals a little bit smaller, and just making more of them until we got to the point where the width of each one of them was 0. And that's how the limiting thing was going on, and that's where Leibniz and Newton kind of like put it all together. But before that, they were adding up a bunch of small little pieces together, and it was getting cumbersome trying to write it all into one. So actually now we're going back in time. We've already shown you how to do most of the integration that you need to, but we're going to show you what led up to that integration and what started the integration ball rolling. So let's go ahead and talk about sigma notation. Alright, sigma notation. You're going to use a capital Greek sigma, and it means sum. So it's like a capital S. And obviously sum, it makes sense, with sum with a sigma, S. It makes a lot of sense. The sum of n terms, a sub 1, a sub 2, a sub 3, a sub 4, all the way up to a sub n, is written as sigma notation I equals 1 to n of a sub I. And that would equal the first term plus the second term all the way up to the nth term, where I is the index of summation and a sub I is the ith term, yes, that is ith term of the sum. And the upper and lower bounds of the summation are n, that's the upper bound, and 1 is the lower bound. So go ahead and pause that and write that down if you need to, and I'm going to move on. Next screen, please. There we go. Alright, find the summation of I from I equals 1 to 6. So we're going to replace the I with a 1, and then with a 2, then with a 3, then with a 4, then with a 5, and then with a 6. You're going to add all those up, and hopefully if you add those up right, you're going to get, oh, I don't have it written down. Wow. Thought I had that in surprise mode too. Wow. The sum would be 21. Alright, let's try another one. I equals 0 to 5 of I plus 1. Okay, so we're going to start at 0 and replace that I. Hey, guess what? We're going to get the same exact sum. There are different ways of representing the same thing. I know that's crazy weird, but it is what it is. And let's try the last one. J equals 3 to 7 of j squared. So that would be 3 squared plus 4 squared plus 5 squared. And you know what? I don't even know what that is. If you're curious, you can go ahead and figure that out. I don't have time. I've already got 5 minutes gone. I only have 10 minutes to get the rest of this done, because I rambled on at the beginning, so I got to move on. Hey, wait a minute, I'm rambling. Move on! Alright, summation properties. If there is a k in front of a sub I, you can move that k out in front of the summation, figure out what the summation is, and then multiply the result by k. Think about it kind of like this. The integral of 3 cosine x dx. You can move that 3 out front like that. Okay? That's what's happening. You can move the 3 out front. Or, if you've got the sum or difference of two different functions, you can find the summation of both of those separately and then add them together. There's another property that happens with summation. Some more properties. Alright. If A is less than or equal to n, A is equal to less than or equal to n, which is less than b, then the summation from A to B, you can separate that up from A to n and then from n plus 1 to b. Okay, that's another cool property. And we've kind of done that already at least once in your homework this past week. Alright, let's move along. If you are going to find the summation of a constant, it's just going to be if the index starts at 1 and goes to n, it's just that constant times n. Because you're going to be, here, let me show you an example, please. Alright, the summation of I equals 1 to 6 of 4. What is that saying? Well, it's just saying add 4 plus 4 plus 4 plus 4 plus 4 plus 4 6 times. So it's 24. Alright? I equals 1 to n. Okay, this is the summation if you're just adding a very simple function. If it's just like I, then the summation from 1 to n is going to be n times n plus 1 divided by 2. Alright? That's just a cool little formula to help you figure out the summation without having to add them all up. Because if I went like this, say I equals 1 to 100, and ask you to find out what the sum of the first numbers from 1 to 100 is, I don't want you to spend 50 hours adding those up to get the sum 50-50, when you could instead just multiply 100 times 101, get that product, and divide by 2 and get 50-50. Ask me about this in class and I'll tell you a little story about adding the numbers up from 1 to 100 and what one sophisticated mathematician did when he was really young. Oh, I have less than half my time left over. Got to move on. Okay, here's a couple more formulas for you to write down. A way of finding the sum of squares. And I'll just let you write that down. And the way of finding the sum of cubes. Like find the sum of the first 10 squares. 1 squared. 1 squared plus 2 squared plus 3 squared, all the way up to 10 squared. This is the formula you could use. Same thing for cubes. And I'm going to let you copy them down, and we're going to move on. So I'm moving on. So if you need to pause, stop rambling, man, and go. Alright. Example number 1. C sub k equals 2k minus 1 for all k. Find the summation of k. Okay, k is the index now. K equals 1 to 3. So I'm going to put 1 in for this. 2 times 1 is 2 minus 1. That would be 1. Plus, now k is 2. 2 times 2 is, that would be 3. And now k equals 3. That would be 5. The sum of the first 3 numbers there, that would be 9. Quick, move along. Go ahead, I dare you. Example number 2. Suppose f of x equals 0.01x, 0.1 e to the x squared, and suppose c sub k equals f sub k, f of k for every k. Find the summation of k equals 1 to 4 of c sub k. So we are going to do 0.01 e to the x squared, so that would be k squared, that would be 1 squared, that would be 1, plus 0.01 e, k is now 2, 2 squared is 4, plus 0.01 e, 3 squared, that would be 9, plus 0.01 e to the 16th power. And when you add all those up, it ends up being 88,942.70921. I did it this way: 0.01, and then I just added e sub 1 plus e sub 4 plus e sub 9 plus e sub 16. No, e to the 16th. Wow. Can you tell I had caffeine today? And multiplied that sum by 0.01 at the end. Quick, move along. I've got less than 4 minutes. Example 3. Represent the sum of all the even numbers from 20 to 50. So k equals 10 to 25. This is the way I'm doing it. 2k. There you go, because that will double them all. 20 plus 22 plus 24. I should have probably given you a little bit of time to think about that one. I'll do that on the next one. Sorry about that. Okay. Represent the sum of the squares of the first n integers. And I am going to pause it, and you're going to try to figure it out. And then you can go ahead and come back in and see if your answer equals mine. Alright, ready? Go ahead and pause. Alright, the correct answer is k equals 1 to n of k squared. That wasn't too bad. And the last example of the day, I think I'll actually get this in on time. Let's go ahead and move on to the last one. Represent the sum of 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6. How many terms are there? Ooh, good. There are 5 terms. So k is going to start at 1 and go to 5. Okay? Now notice that the numerator doesn't change. So the numerator is going to be a 1. The denominator is 2, 3, 4, 5, and 6. And those are all 1 more than the index. So k plus 1 in the denominator. Alright, and then we need a light switch so that it will switch on and off between positive and negative. And I'm going to let you think about that one for a minute. Alright, and then go ahead and think about it for a minute and see if you can come up with a way for a light switch to go on and off so that it goes from positive to negative. Alright, so I'm going to give you just a minute on that to think about it. How can you make a light switch so that it alternates between positive and negative back and forth as you're adding? Well, did you get it? I don't know if you did or not, but the easiest way to make a light switch is to put a -1 in there. Alright, and let's see here. We want it to be positive on the first term. So we need to make the exponent k plus 1. Because then we'll put a 1 in there, and that'll make it to the second power. That'll make that a positive 1. And then for the second term, this will be the second term, we'll put it, it'll be a 2. 2 plus 1 is 3. And that will be to the third power, -1 to the third power. Hey, that works out. Anyway, this does conclude Definite Integrals, Part 1, Sigma Notation. Hey, by the way, ask me about the light switch question in class. It's a cool little riddle. All right, peace out.